Hi, folks. Last year, April 1st, 10 minutes past midnight, I get a call. Hey, Martin, our database is unresponsive. This is like a V database. Some things that we use to run all our production on. So I go, log in, see what's going on. The AWS instance on which this database is running is unresponsive. Okay, I'll check it out. What's going on? No, nothing really. Okay, I'm going to do a restart on this instance. This is a big old i3 instance with a local SSD drive running MongoDB in a replica set mode. So it's a cluster. Shut down in the hopes that it will come back up. Guess what? It does not. So next, okay, let's do a failover. I have this standby node, and this should automatically take over. And I do a failover. And you think the failover worked? No, not really. Turns out the failover database had been configured with slightly less resources and simply wasn't unable to handle the traffic. So we had a third failover, but that too did not work. Then what do we do? Okay, MongoDB has this really great replication set mode where you just add a node to the cluster and it automatically pulls the data from one of the surviving nodes and puts itself up and becomes functional. So I did that. Did it work? Not really. So it turns out this is a 5 terabyte database and pulling this across the network takes some time. And after an hour, it had pulled a terabyte or so. But this time it's like about 4 a.m. in the morning and I'm like getting out of options. So, okay, I turned it back up and eventually by 9 a.m. in the morning, we get the database back. So did we learn something from this? Something. So do you think we still have this big old database and are we running production on it? Yes, we do. But what we have done in the meantime is we've done a bunch of things to make the manageability of this database a bit better. First, my name is Martin. I work in Starship. I'm working in site reliability team. We are running the infrastructure for Starship. So this is databases, monitoring, like load balancer, all that kind of stuff. So Starship is trying to revolutionize ground transport by using autonomous delivery robots. The robot is about like yay big, about like a little bit bigger than this speaker, and drives at pedestrian speed on sidewalks. So you may have seen those in Mustamäe. They are delivering food and stuff from like Selver and Ulits, burgers, and so on. So it's a small operation here at Mustamäe, but also there is a way bigger deployments across the world, specifically in US. We are present in multiple university campuses, multiple corporate campuses, industrial campuses, and so on. And so far we've been done about 200,000 commercial deliveries, and the robots have driven quite a distance. Like I think the recent was, but if you think from here to moon and back, so that's about as much the robots have been driving. So quite a lot. So still growing. And but then what makes this robot drive? So there's quite a bit of intelligence in the robot. So it's like neural networks trying to identify what are the pedestrians, where there's a sidewalk, what do I do? What if there's like say a bicycle coming, do I dodge the bicycle? Do I run into it? What's going to happen? So these are local decisions and those are made on the robot. But then robots have no awareness of the surrounding world, like the world at large. They don't know where is customer, where is delivery, where to drive. So all these routing decisions and fleet management and the delivery optimization happen on the back end. The back end is on AWS, and we run most of our things on Kubernetes. It's the exception of databases where we are running in just instances. And it's a heterogeneous environment. We are running mostly Node and Go, but with some mix of C++ and some Rust thrown in measure. And this database, it's a large monolith, and this has quite a few challenges to run this. So please raise your hand if you've worked with MongoDB before. So, okay, so some people. So MongoDB is a document database. It has a really flexible schema. Some say it's schema-less, but no, it's not entirely true. There's always an implicit schema there, so you have to organize your data somehow. Instead of tables and rows, you think about collections and documents within that collection. A document in the collection can be totally unlike another document in that collection. So there is some freedom there. The query language is very simple. It's JSON-based. It usually operates on a single collection. You have usual operations like find and insert and delete and all that. And the documents themselves are also like a JSON-like document. In general, they are stored binary JSON. It's called BSON. It has pretty good performance, usually like because the query language is so simple, there's nothing really there to optimize. You just, okay, so you query, pick the right index, and off you go. So it's like most simple queries go and finish under 1 millisecond. You can shard it if you want, so that's an option. We are not sharding it. And so it's really like the HA support is pretty good with replica that you like can set it up quite easily, and it does handle automatic failovers. What is not so great is this whole observability. Like, do you understand what's going on in the database? I think that's like it's good enough if you have like just a handful of applications in a small database. However, if you start adding hundreds of applications and your database grows, this is really not enough. What's like, is available out of the box. So, like, what is there, and what we want to be there. Of course, you have your basic tools. You can run your like find queries, you run your explain plans, you understand what's the resource visit of the query, block information, and all that. So there's also a profiling option. You can set the database in a profiling mode, and in this mode, you tell it like, okay, profiling is all those queries that are taking longer than n milliseconds. And then this logs all those execution plans into a system collection, and you can query this and get an understanding of the slow queries. What's the problem with that is, like, you really cannot reliably use wall clock to measure query performance. Like, imagine you have tons of transactions going on in the database, and most are like under this slow query threshold, and suddenly you start a batch job that starts to hammer on the database. Now, those harmless queries that were going under 1 millisecond might now go above your threshold, like they might take 10 milliseconds. But it's not their fault. But when you go and look now your system profile collections, you think, oh, those are the bad queries here. I need to go and optimize them. In reality, it might be your actual batch job that is giving you problems. But this is not totally obvious from this approach. If you just use wall clock to measure, it's much better to use some resource usage metric like documents visited, index keys scanned, or blocks read from disk. But like by default, that is not there. However, what you can do is you can turn on full logging on the database, and it will spit out like loads and loads of JSON data into the logs, which you can then go on and parse and understand what's, okay, how is my application using the database, what are the execution plans, and how this all is fit. The problem with that is that, okay, it's nice. The first problem is it's difficult to parse. It's a kind of irregular format, and you really have a hard time of writing a parser for this. The other problem is that you might be doing like 100,000 transactions per second, and then you have to parse all the execution plans and the query output of this 100,000 transactions, and that's not very realistic to do in real time. Well, it is if you put some resources on it. And we use logging quite a lot. We actually did implement that parser, and we are trying to parse these messages to get some understanding of what's going on in the database. And we also set a lot of metadata when connecting to the database, so that we set an app name, so we know that, okay, this is the application that is using this biggest collection in some bad way. We have our applications mostly instrumented with Jager Tracing, so that we can get a full understanding of, okay, here's the request coming in from the mobile application, going into this microservice and into this other microservice, and finally landing in the database. So Jager gives us a pretty good picture of what's going on, but it is a big investment, especially when you want to instrument your existing code. So you might think that there's like a database call, some like deeply nested in the code, and you need to give it a trace header so that it would be a useful trace. So, but what if instead we could have a database-aware service mesh thing? when we have applications talk to the database, we would have the service mesh capture this traffic and generate metrics for us and do some of the tracing work for us. So this would be almost for free for us. We put this service mesh into place. It tracks the application's database usage, and it's awesome. The sad thing is that today such service mesh does not exist. So we can try out Istio, which uses the Envoy proxy, and Envoy actually did have a MongoDB protocol handler for like a couple of years ago, and they were able to generate MongoDB metrics by just looking at the traffic that the application sends to the database. However, MongoDB decided to upgrade their protocol, and thus Envoy's and parser no longer works. And we considered, okay, we could take this Envoy and add this our own plugins there and get MongoDB metrics this way. But it turned out to be a somewhat difficult to do. It's a large C++ code base and takes 2 hours to compile, and then like it's a lot of foreign code and not really feasible for us. But what we figured is that this MongoDB wire protocol is not that complicated because it uses like little JSON-based messages. It's like quite easy to parse. And okay, we'll do our own. It's not a big of a deal. And then, okay, you want to roll your own MongoDB transparent proxies that captures all the database traffic and then generate some metrics and traces for you. What's like, there are some requirements there, like implicit, like, okay, it needs to perform well. It doesn't need to have it's a predictable performance. You don't want garbage collection pauses there. You want this thing to be, most of all, it needs to be correct. And what are the options here? Like you have a couple of languages, like where you could use this, most notably C++ is one, but we have a better option in this center, which is the Rust programming language. So this was invented in Mozilla about 9 years ago or so. Mozilla has this big old browser that has all those like memory corruption issues and CVEs resulting from memory safety. So they figured out, okay, like we really are struggling with those memory issues. Can we have a language that does away with all this memory safety issue? And then they put some thought into it and figured out that, okay, we can do much of this checks in the compiler so that whatever you do, the compiler makes sure that your code is already memory safe, free from data races, double frees, and dangling pointers. And that's what Rust does. It guarantees you memory safety. It doesn't guarantee you that you don't leak memory, although it also helps that a little. What this means for you as a developer is that the compiler is really strict, and it's gonna like prevent you from shooting yourself in the foot, and you'll end up fighting the compiler a lot. Okay, what do you mean I can't use this? You can't do this because you're leaking memory. You can't do this because this reference is lost, and then or the data that this reference points to is lost, and you will be using the bad reference. So it automatically detects all these kind of issues and does away with like a class of issues, which is the memory safety, which is kind of good. If you get it to compile, it probably works. So that's the premise. And the other thing is, it's like the zero cost abstraction. You can use like nice abstraction and be relatively sure that it will compile to fast code. And here's an example of this. How do we parse MongoDB protocol header? So every MongoDB message is preceded by a header, which is the size of the message and then the type of the message and some other bits. So the type, like once you get the header, the next thing will be the bytes, which is usually a piece and payload, which is like quite easy to parse. So in this example, we read a message header from a buffer actually, and we check for errors. We convert this to little endian format and then we return this. This is a nice, concise error handling. This question mark means that if this call fails, return early with an error. And otherwise, it goes, this okay thing returns the full header. It's really concise. Otherwise, you'd have like some 8 lines of code added for just the error check. And this being Rust and the new thing, I'll do this as a moonlighting project, like on weekends and rainy days when there's nothing to do outside, and spending like 1-2 hours a day maybe. And after 2 months, I have a working TCP proxy, thread per connection, parses the MongoDB protocol, times and measures all the requests, emits Prometheus metrics, doesn't crash, reasonably good memory usage, CPU is really good, and put it to production, still doesn't crash, but then you discover like a couple of bugs, something related to like MongoDB being inconsistent, how it uses like camel case and snake case occasionally in command names. Another with just me forgetting TCP no delay, which added like a bunch of latency to each call, and an interesting thing about how malloc handles thread allocation. So there's this thing called arena, which keeps floating and floating up until you run out of memory. So, but luckily you can tweak that with a environment variable. So fix that, and then decide to run this as a sidecar in a Kubernetes. So as I said, we are in a Kubernetes deployment, so we have we're good to use sidecar. So sidecar is usually like a little tiny additional containers that you bolt onto your application, and it can handle like things like sending logs to some collections, collecting telemetry, proxying some traffic. Jager traces can be collected with a sidecar agent, and you might run like a bunch of these on your deployment. And you can have as many as you need. So there's a small issue with like this current Kubernetes version. It really doesn't enforce the order of how your application starts up. So first you have your init containers, then you have your other containers, and they start up in some random order. So it might be that your sidecar is starting up later than your application. And if you're relying on the sidecar to do some work for you, it might not be ready to do that work. So what helps is to retry in your app, or more pragmatically, put in a 3-second sleep in your application startup. That's what we ended up doing for the most part. But yeah, when you run many sidecars, you will find that your app will crash and start up because it can't connect to the database, it can't connect to another server, or so on. And why this happens is that how we run, for example, this Mongo proxy is that we have an init container that grabs the MongoDB traffic from the standard 2717 port and forwards it to the proxy. So this init container is guaranteed to be the first thing that runs in your application. But then the next step, like either the sidecar or the application itself, it's sort of like anybody's guess which one is going to be starting up first. And if the app gets there first, it'll get the connection refused because the proxy is not there, but the traffic is already sent to the proxy. So what you need to do is just retry or sleep a little so that the sidecar can get there first. And so that's what we do. We redirect all the MongoDB traffic to the proxy. Application is totally unaware of this. They are connecting to this MongoDB that say it's configured in the command line or configuration, and they still think they are connecting to the MongoDB. But magically, it goes through the proxy. So the proxy then tracks all the metrics. Okay, you have a request going to the database. Note what the time was. You have a response back to this. Note what the other time was. Put it in a histogram and expose in Prometheus metrics. And so in the same way, you would count bytes and whatnot. Documents, inserted documents, updated documents returned, and you get a pretty decent overview of what's going on in the database from client's perspective. So how do we inject this sidecar to the application? You have this option of like going in and writing like a ton of YAMLs that adds this additional container with its resources and parameters and all that. You can do this, but a better way is to use some configurable sidecar injector. And we're using the Tumblr one. It's what you do is you put your sidecar configuration in a config map and then tell your application via annotations that, okay, load this MongoDB sidecar with the application. And then it's rest is like happening magically. There's an admission controller that intercepts when you try to deploy your app, and then it patches in the sidecar context. This works quite well. But if you have like some specific requirement, like what they say, maybe you want to add some custom labels to the app, and then you probably would have to roll your own. Or if you want like to say, okay, in this namespace, I want all the apps to have this proxy in this configuration. So this Tumblr injector might not have the flexibility. But for us, right now it's good enough, convenient to use. And then how do you scrape? We use Prometheus operator from CoreOS. It creates a custom resource in your Kubernetes, and then you can do just create me a Prometheus. It will set you up a Prometheus instance, and then you have this thing called service monitor by which you tell Prometheus, like, okay, use these labels to find those items to scrape, and then Prometheus goes on and reconfigures itself and starts pulling all those metrics from the deployments. Quite convenient to use. Unfortunately, if you make a typo somewhere in this endpoint section, you might end up in like a situation where you have to debug this for a couple of hours because it's somewhat non-obvious. What's like, is all these sidecars, like what's the impact on my application? Like, how much CPU or memory I have to add for this? So with the MongoDB proxy, it's quite tiny. It's like a 6 megabyte binary. It runs on a minimal Debian. It runs on Alpine if I get static linking to work properly with Rust. And response latency for like smallish payloads up to, let's say, 64K is unnoticeable. From there, it might add a millisecond or two, or maybe more if the payload is really huge. This goes into the BSON parsings that happens in the sidecar. And if you look at the examples, these are like some actual Starship applications that handles deliveries, I guess, has 3 sidecars attached to it. One is Jager agent that's collecting the trace information. Another is Linkerd proxies. This is the Linkerd service mesh. My favorite service mesh because it is so easy to configure, and you just install it and it gives you good metrics out of the box. I like this a lot. And the usage here is actually in like millicores, and like 1,000 millicores is a single core. So this app uses about like 450 millicores, and this Mongo proxy uses 1.6 millicores. It's like 1.6% of a core. Is quite tiny usage, I would say. And the memory, like with this, it depends on how much you put data through it. It has to currently load the whole BSON into memory for parsing it, so it can go higher. But for typical apps, it's like tens of megabytes. So for this like 3 to 5% CPU tax and some memory, you will get metrics. And the metrics are whatever you can measure from client to the database. So you will get from the upper left corner, this is again one production Starship app. Okay, you get like a documents return per second. This is like rows returned from a single query or like a single collection. So in this case, like 115, it's not that bad, it's probably okay. But then if you see what's the byte returns by collection, so it's a single large collection that we're pulling like about 5 megs out of every second. So this, like, even the business metrics, if you know them, okay, we are doing the N amount of deliveries. Is this reasonable? Probably not. So I might look into that. Next is documents changed by collection. So again, like this is reasonable, aligned with the business metrics. Response latency, it's a bit hard to read without hovering over and seeing the tooltips there, but the majority of the queries here are like under 1 millisecond, and suddenly there's a bunch of them that are over it. So there's a clear like line between there. And finally, in the lower row, how many bytes returned by operations total. So this find and modify seems interesting, like 289 gigabytes fetched in this time period. That's quite a lot. I would go look into that. And then the 99% latency by collection. So there is this single one collection that stands out. So based on this, I would go into the application, identify probably this find and modify operation on this collection. We do have collection names. I just had to omit them, so it's not visible here. So you'll find what's your collection name, what's the operation on this collection, what are they doing, how often, and then you go in and optimize. And once you've done that, then you have like we teach that for some time, and we cut like a bunch of cheap CPU off the applications and bunch of CPU off the database. So it was really useful for that. And the other thing, what you can do, but it's not that great to do automatically, is you can do Jager tracing. So you can have this proxy do Jager tracing for you. But like in the simplest case, you could, okay, you get a query into the proxy and you can start a Jager trace from it, and you can load this and annotate the trace with the query and response and timings and all that stuff. However, for this trace to be really useful, you would need to have passed in the parent trace of this, so that you get this full stack from your mobile app to your microservices and to your database. But this passing this trace ID in is not automatic, and it probably never will be. But well, never say never. So you still need to go and instrument your application, and there's no way around that. We are for this we are using open tracing APIs, and we are using the Jager operator to deploy Jager and some collective traces, and has helped us a lot when troubleshooting the production issues. And then I think we are at the end. The summary nowadays, like the monolithic database is a great thing to have. Like it is simple to run somewhat. Like if your applications are like under control. You don't have to worry about sharding and replication and data consistency. It's all in one place. You can like run transactions across it. It's nice. Once you, however, cross some limit and you have lots of applications using the database, it can become a nightmare. And we are kind of pretty close to that when we have like large issues with that, and then we do some additional like stripping down the monolith and coming up with plans to move this data outside. So it can be convenient to start, but in the end, it's a lot of trouble and a huge risk. And well, having this sidecar thing for monitoring database is pretty convenient. However, you still need to have your conventional tools like your query plans and index stats and table stats and all that. And with that, thank you very much for listening. There's a bunch of links for the things you mentioned, and I believe we have some time for questions.
Hi, everyone. Thank you for the presentation. It might be a little bit off topic, but I wonder if you can tell us a bit more about how the robots actually work, like what kind of data is on the robots, how do they communicate with the servers, and so on. Like, can you tell us something about that?
So I don't know how much I can disclose here. So, so one thing is that robots are mostly autonomous, but they do run into trouble occasionally. And like someone might have parked a huge truck on the sideway and you can't just get past it. Or there is a typical road crossings that you cannot do automatically because you don't see enough. So robots has to have a server connection to have an operator come in and see what the robot is doing. So robot sends video feed constantly to the operations. So when you can see always how the robots are driving and what they're seeing, and you also have like some radar information. And so it's also like it collects lots of telemetry, stores it locally, uploads it later. So this happens. Like I think we are generating gigabytes, tens of gigabytes maybe of data per robot per day. And then we do like end of day sync and upload all this telemetry. And then what this does, okay, we have lots of pictures and videos, and this goes to the machine learning team, and they run their models and do their own thing. So there is no MongoDB on the robot, but the robots are highly dependent on having MongoDB available. For instance, like any drive commands that the operator might send to the robot are going through MongoDB. So we're actually using the database as a messaging system as well.
Thank you.
Thanks so much. So tracing is also automated in your case?
So tracing is not entirely automated.
Okay. In some degree?
No.
Okay. So basically you don't have another database about tracing issues.
So we have right now the ability to collect traces from this proxy. However, what we haven't done is that for those traces to be useful, we need to have the parent trace. And then passing that parent trace in is the things that cannot be automated.
All analytics in the heads of your team members, basically, as I understand.
Sorry, can you repeat?
All analytics in heads of your team members, basically. There is no something, no models created on analytical level, which you visualize and you can share it.
So yeah, other than the basic Jager UIs that we use for distributed tracing and the Grafana dashboards that we have the metrics like first. There's no UI per se. But what you can do, like you can go and query the metrics from Prometheus and use those.
Okay, thanks.
Who else have these things to throw around?
Thank you for your presentation. You mentioned a problem in current version Kubernetes that application and sidecar can start in a random order. But what about ending? Do you have a graceful deployment, and how do you handle a graceful deployment with the two sidecars with one application?
We actually do not.
Okay.
So we, like most of our apps, even have not like a graceful termination configured. And those that did try this immediately ended up with having issues with sidecars. So again, it's something that needs to be worked around. It's like the sidecar support presently it's not that great in Kubernetes.
Okay, thank you.
Thanks for a great presentation, Martin. Simple question. Are you trusting Kubernetes enough to run MongoDB on it, or you are having big badass servers running MongoDB separately?
The short answer is no. I would like to, though. Like I would like to have Kubernetes in a state where I can trust it with my databases. So I would be very happy if that happened. But as it is, as this monolith right now, we need to break it down into smaller bits, and then once we have it down to like manageable size, I'd be happy to put some of those chunks into Kubernetes while leaving the rest of the monolith on a traditional instance.
Someone else? Questions?
Thanks for the presentation, really interesting. Any plans or possibilities or thoughts about extending the usage beyond MongoDB to other similar document store databases, for example?
So that's an interesting question. One area to explore is to, okay, what does Linkerd do? And the Linkerd has this open issue. Okay, what if we could parse MongoDB? What if, like, they have this automatic protocol detection. They try and listen in on what you're talking to is between the applications, detect what's going on, and then passes through and like a filter that handles this kind of traffic. And so this is like a request to do this for Kafka, Postgres, Mongo, and like, okay, maybe I could take this Rust code and chuck it into Linkerd, and maybe that would be a MongoDB adapter, and then someone would add a Postgres adapter, and then someone would add Kafka, and I think that would be really, really great. So there is a discussion that, at least in Linkerd, is that, okay, we want to do this, but it's not clear yet how. So I'm really like following that discussion. I mean, this is really interesting.
Okay, thanks.
Thank you so much.